Welcome to your pre-lab exercise on atoms, elements, compounds, and chemical bonds. Today we will be looking at the definition of matter, investigating the relationships between atoms, elements, compounds, and minerals, and you'll be introduced to the concept of chemical bonds. A mineral is narrowly defined as a naturally occurring, inorganic crystalline solid with a fixed chemical composition and characteristic physical properties. By this definition, substances such as ice and diamonds are considered minerals, whereas water and synthetic or lab-created diamonds are not. We will explore this further in class. A mineral's physical properties are a function of its chemical composition, the elements and ions that make up the mineral, and the chemical bonds that bind them together. The physical characteristics are important because they are the key to identifying unknown minerals. Matter is an ill-defined general term for everything around you, anything that has mass and takes up space. The computer on which you are viewing this video is composed of matter, as are the carrots you ate for lunch today and the air you are breathing. Matter has four readily recognizable states: solid, liquid, and gas, of which you are likely familiar, and more exotic forms including plasma, which is the ionized gas as found in fluorescent and neon lights, and matter in the sun and stars. Minerals are compounds, that is, they are composed of one or more atoms bound together by chemical bonds. Mineral characteristics, which may be diagnostic, are a function of the atoms that form the mineral and the types of bonds that hold those atoms together. We will look at the different types of bonds and how they influence the physical characteristics of minerals so that you may better understand mineral identification. An atom is the basic unit of matter. Atoms comprise three subatomic particles: protons and neutrons, which together make up the nucleus, and electrons, which orbit the nucleus. Protons are positively charged particles, the number of which defines the element. For example, oxygen atoms have 8 protons, carbon atoms have 6, and hydrogen has 1 proton in the nucleus. The number of protons also defines the atomic number. Neutrons have no charge. The number of neutrons in an atom determines the atomic mass number, or the isotope of an atom. Hydrogen, for example, can exist in 3 isotopic forms: protium, which is just ordinary hydrogen that contains 1 proton and no neutrons in the nucleus; deuterium, which contains 1 proton and 1 neutron; and tritium, which contains 1 proton and 2 neutrons. Neutrons weigh about the same as a proton, so a tritium atom is heavier and has a higher atomic mass number than protium or deuterium. Isotopes are important when it comes to absolute dating, which we will explore later in the semester. Electrons are negatively charged particles and orbit the nucleus in a cloud. They occupy different orbitals or shells and are the particles that form chemical bonds. The diagram on the left shows simplified shell models for several common atoms and their electron configurations. A blue circle represents the nucleus of each atom, but remember that atomic nuclei are made up of protons and neutrons. The table on the right shows the symbol and atomic number for several elements, as well as the distribution of electrons in the orbitals or shells. Note the number of electrons in the second, third, and fourth shells. The second orbital can accommodate up to 8 electrons, and the third shell can accept up to 14. Some of the listed elements have electron vacancies and can accept electrons from other atoms. This is how chemical bonds are formed. Compounds and elements are formed when multiple atoms combine to form a substance. These atoms are bound together with chemical bonds, which have varying strengths. There are 4 types of chemical bonds, and bonding can be achieved in several different ways. The 4 types of bonds are ionic, covalent, metallic, and van der Waals. We're going to explore all of these bond types in the next slides. Ionic bonding involves the transfer of electrons between atoms to complete vacancies in electron shells. Ions may be positive, cations, or negative, anions, and are attracted to opposites. Figure 4 shows the ionic bond formed when the negative chloride ion bonds with the positive sodium ion to form sodium chloride, or common table salt. Ionic bonds can be quite strong. This diagram shows the relative sizes of the sodium and chlorine atoms and their locations in a crystal of halite. Covalent bonds form between atoms when their electron shells overlap and they share electrons. These bonds form when atoms of the same element, for example carbon, cannot bond by transferring electrons to each other. Carbon, which forms the minerals diamond and graphite, has 4 electrons in its outermost electron shell. This shell can accommodate 8 electrons, and so adjacent carbon atoms share electrons, thereby filling up the outer orbital of each atom and creating a very strong bond. Note that diamond is the hardest known substance. This is a consequence of its very strong covalent bonds. This figure shows a simplified carbon atom. The outermost electron shell contains 4 electrons and has 4 vacancies. There are, therefore, 4 vacancies that can be occupied by electrons from another atom. This simplified diagram shows overlapping electrons in diamond, forming covalent bonds between adjacent carbon atoms by sharing electrons, and completing the outer orbitals of all the carbon atoms. Covalent bonding of carbon atoms in diamond forms a 3-dimensional framework. Metallic bonding also involves electron sharing, but in a much more extreme way than we see in covalent bonds. Electrons in the outermost orbitals of metals such as gold, silver, and copper move readily and easily between atoms and form an electron cloud. This electron mobility accounts for the metallic luster or shininess of metals and also their good electrical and thermal conductivity. Here we see negatively charged electrons forming a free-floating cloud around the positive metal ions. They don't belong to any one metal ion. This electron cloud gives metals their extremely good electrical conductivity and also explains other physical properties of metals such as malleability, the ability of a substance to form thin sheets, and ductility, the ability to draw metal into a wire. Van der Waals bonds are relatively weak attractive forces that operate on electrically neutral atoms or molecules. The attraction is due to momentary electrical polarization of atoms or the creation of temporary fluctuating dipoles by the movement or distribution of electrons within their orbits. Graphite and talc, which are both very soft, slippery minerals, are examples of minerals with van der Waals bonds. In graphite, which is also composed of carbon, but in a different crystal configuration than diamond, covalent bonds between carbon atoms form strong sheets, but the sheets are attracted to each other by very weak van der Waals bonds. This is what makes graphite so useful for pencil leads. When a pencil point is moved across a piece of paper, small pieces of graphite that are only held together by very weak bonds flake off and stick to the paper, allowing us to write. So, to summarize, minerals are defined as inorganic, naturally occurring solids with a fixed crystal structure and a fixed or fixed within limits chemical composition. Each mineral has characteristic physical properties which can be used to identify them and which is a function of the atoms that form them and the chemical bonds that hold those atoms together. There are 4 types of chemical bonds: ionic bonds, which form when electrons are transferred between positive and negative ions; covalent bonds, which form when atoms share electrons to complete outer orbitals; metallic bonds, which are formed when free-flowing electrons form clouds around cations; and the weakly electrostatic forces that form van der Waals bonds. Each of these bond types contribute to the diagnostic characteristics of minerals. This week in class we will be looking at chemical composition and mineral groups, the physical characteristics of minerals, and learning how to identify minerals based on their physical characteristics. Please bring a device to class, a phone, a tablet, or a laptop, and be prepared to engage. See you in class.